Okay, so today we're going to do things a little differently. Instead of 45 minutes for the problem, I'll spend 35 minutes on the problem, so that way I will have 10 minutes to talk to the interviewer. Of the 35 minutes, I'll probably use about 30 minutes to actually work on the problem and 5 minutes to make any last minute changes. We've done the social media. Design X. So let's do chess. Poker's got a lot more. I know chess slightly more than I would know the rules of poker, which is why I chose chess. Okay, one. Let's see the questions that I would ask. Right. First thing would be, do we support multiplayer? There's no mention of multiplayer support in the question. So this is what I would ask: do we support multiplayer? If we have to support multiplayer, then there's a lot more details that go into it. So if it's just a single player game, then that means you're playing against the computer, which means you can just it's a simpler computer program at that point. So you would have an algorithm which can calculate what the next move for that particular position is. You would have a database of moves, a database of positions and moves. So from that database, it's okay what you would be able to say based on this, what will the next one be. Or you could connect to open source models which already exist. So you have algorithms for algorithms that are meant to play chess. So you can just connect to one of those endpoints and use that. So at that point, it becomes you designing just the front end or the user experience more than the actual system. So majority of the system is the algorithm, which is very specific for the game. So So the question is, do we support multiplayer? I'm assuming the answer is yes. If we support multiplayer, then the next question becomes, do we do multiplayer over LAN, or over the internet, right? Essentially, it's more or less the same concept. If it's over the LAN, you're not dealing with you don't need to deal with the central server. It's going to be computer to computer in the same network. So one of them can be the host and the other one can just be a client that connects to the same host. But if it's over the internet, then it has to go through a server at some point. So you could have client to server to client, or you could have a client to a client, but the connection is established through a server. So sort of a peer-to-peer connection. So, but for that to be established, you would initially need a central server. So that's the difference there. I'm assuming that it's going to be over the internet. That's the assumption here. The next question that comes to mind is, it's a question of, if I'm assuming this is a platform, right? It's not meant for one game. The system's not meant for just one game. So I'm assuming it's a platform like chess.com or Chess, one of those. The assumption is it's a platform. Yeah, so in that case, we would go into how many users, active users for the platform, and and how many games. So you would go into peak user activity in day, and that's so we will have to talk about the peak user activity in a particular day. So you could have a couple of hours in the morning or in the evening when people tend to be a lot more free, so they had a lot more free time to open an app or open the website and play a game of chess. So you could have a particular time in the day when there's a lot more users and a lot more people playing games. So that's question 5. Then okay, for now we're not going to deal with other things like analysis of games that have been played, or just learning resources, puzzles, and all of that. That's something that is slightly beyond the scope of this, but that's something that can be done. So for now we'll just focus on these. So the question becomes daily active users, right? Again, for this we will have to store user management, user auth, that's standard, and on top of that you would have game mapping, as in user mapping for user matching the game. That's one thing. And once you have the game matched, you have game data. So that's that'd be moves and game ID. That's about it. And outcome. So that's something that you would have for game. User management, user auth. Okay, hold on. User management would be your usernames, passwords, hash password, and usernames, hash passwords. Other info, you could have a bio, and on separate tables you could have user data, things like game history, all of that. You would have game history. That's about the users. And user auth would mostly just have usernames and API, not API, auth tokens. So that's not game data would have this. So okay. That's about the game data. So there's nothing else that we would need to store. I don't think so. That should be good. So now count the daily active users. Let's just say we have let's say 100,000, 1 million users. 1 million users, and each one, let's assume on average plays 3 games a day, right? Actually, 3 games on average. Let's assume that at peak usage we have let's say 800,000 users. Actually, that's 800,000 users. So 1 million users, let's make it 10 million users, and this would be about 8 million users would be peak. Let's right. So in total, you would have about 30 million. Total would be 30 million games a day. So over 30 days, that would be 900 million. Oh, sorry. Yeah, 900 million. 900 million games per month. And that's roughly about 108. Yeah, that's 108 million games per. No, what am I doing? 10.8 billion games per year. Right. So that's how much memory is stored per year. And let's say there is we're going to save this for. Okay. So there's two kinds of memory that we would have. One is long term, and that's going to be the games that have happened in the past. So it's not something that we need to save. So that would be it's not something that we would need to read immediately. So in this case, it will be stored on disk. So all past games are stored on disk. And short term, these are ongoing games. Ongoing games in cache. Yeah, this is again ongoing games in cache, and these would be both read, write. So in general, as a system, it's not going to be. We've seen systems with read heavy and write heavy systems, but this is not one of those. Neither read write ratio is about. You might have a couple more reads than writes, because if let's say you're accessing past games, you would that would be a read only. So let's say 2:1. Yeah. No, hold on. It's not exactly 2:1, because every time a player makes a move, that's written, and the other player must read that move. So that's a read, but it can be passed directly. So yeah, let's just say 2:1, because it's a 1:1 for ongoing games, and let's assume that let's make it 3:1 if let's say both players want to read a particular game. That's about it. 3:1. Okay, so that's for the math. What am I missing? I'm missing storage space, right? So per game, these the username, hash passwords, and user data. Usernames, let's say 20 bytes, and so that hash passwords is going to be, let's say 256 bytes, and user data will do that. So the game history will have let's say each move you have A1, 2, so it's 64 squares, right? So you have A1, 2, H8, I think, yeah, h8. That's the board position, so that's 64. So that's 2 power 6, right? That's 64 squares, 2 power 6. Okay, but let's just write it down as characters. So you will need 3. You need about 4 characters at most to describe one position, and another 3 more characters for you to say what the end position is. So about 7 characters. So let's just say 7 bytes. 7 bytes for game history. For each move. Per move. Per side. So that would mean roughly about 14 characters for both sides. And let's assume a game goes on for 100 moves. So 14,000 bytes per game. That's at most, but that's going to happen. And yeah, so that's for 1.4 KB. That's it. User auth is again usernames 20 bytes. But instead of usernames, we could do a user ID here, which we can just say, since we have 10 million active users, that will work out to a million is 10 power 6, so we would need 2 power 20 for that. 10 million, the closest multiple of 8 is 24, so we would need about 24 would be 3 bytes. 3 bytes. Yeah, 3 bytes. Where am I? Yeah, I can do 3 bytes for the user ID. That should work. Let me make it 4 just in case we're able to. If the system scales up, we would be able to handle over a billion users. So right now we're at 10 million users, daily active users. Let's assume that we have another 50 million inactive users. So that would still put us way under the billion users. So I believe 3 bytes should be good enough. So let's leave it at 3 bytes. So in this case, that way we would have user ID instead, and this would be 3 bytes. And this is something that constantly keeps getting added. So let's say the auth tokens are 128 bytes. And we shouldn't have spent all the time on user ID. Game data. Oh, we've already covered that here. Game data. The moves would be 1.4 KB. And game ID, let's assume we use 4 bytes for the game ID. And the outcome is 1 byte. This roughly is 1.4 KB per game. Since 5 extra bytes is not going to make it a lot, so So it would be 1005 bytes, which is roughly 1.4. Okay, daily active users, we've done that, we've done this. Okay, this is so in this case we definitely know that we're going to need some caching. Now the question is, for this, do we use SQL or no SQL, right? I would say we use SQL for this. So I would say we use SQL for this, since each game is independent of the other games. So yeah, it's going to be, yeah, the SQL makes some sense here, since SQL makes some sense because you have a lot of structure in the data that comes in, and you know that you can save you can save, you can keep the game in the cache until you have to save it in the database. Ongoing games will be in the cache until you have to finally move to the database. So that way, when it's time to move into the database, it's all very structured. So I think SQL works good for this. I would say SQL. So yeah, let's get started building the actual diagram for this. User interface, and this one, let's say we have a load balancer here. And what that does is connect to okay, this one will be user management system, and that would have its own circle, which is the cache. This is purely to check if the username exists at the time of creation, and you'd have a user DB. System, then you would have service. This would be an auth service. This would be an auth service. Cache. Okay, then you would have the auth, you have the username, then you would have games. You could have ongoing games just sitting in a cache. Okay. So the user interface sends something to the load balancer, and at the first go, the load balancer. This is during sign up, right? So user interface makes a request. This is, let's say, sign up. Profile updates, and the user management checks the user cache. Check if username exists. Does that? So that way, if the username doesn't exist, if it exists, it returns that. So this helps in this cache helps with sign up. You won't need multiple it avoids multiple database. Let's check for existing usernames. Duplicate usernames. So that's about the cache. So that's why we have this. And now, if the username doesn't exist in the cache, then the username makes a request to the database. If not in the cache, it checks with the database. And the database responds to the cache. Since the name exists, and if it exists, then the username cache will save that and return whether it exists. Makes more sense. Let's do that. And now that's one way to check for the usernames. Now when there is any updation that has to go from the user management system, so either creation or update of the user data, so that goes directly to the database and fetch from DB. So if let's say we have to fetch some uh, user information from the database, so that's going to go directly from the database instead of getting it from the cache. Moving on to the auth service. The auth service will be, again, in this case, if I have 4 minutes left. Okay, I've got to be quick here. The auth service will right. First thing that you would do is login. So you could have login or validation, auth token validation. So the auth service check if token cache is in cache. Yeah. So it's actually no, I request for auth token. So this checks if it's in the cache, and if it's not, then it makes a request. So it makes a request. This is auth token return, and if the auth token doesn't exist, then auth token, and the validity is determined by this. In case of login, what it does is, in case of login, Okay. Fetch from user. Okay, we're at 35 minutes. Looks like I'll need the extra 10 minutes just to wrap this up. So maybe I will use 5 minutes of that. Let's see. Okay. So I would randomly fetch from the database. So that way I will be able to check if the login credentials are valid, and if it's valid, then I would we're not doing this. We're always reading through the cache and we're not directly hitting the database. Creation or updation is going to go. Creation or updation is going to go directly to the database. And that's that. That's for the hot service. Now for the game, this is the most important one. So I would say the first thing that we would have to deal with is connection, right? So for that we could have a separate service. But that would mean we would have multiple services accessing the same database, like in this case. So let's have one service deal with all of it. So in this case, let's game request. So the game service will get a request, be it a request to a request of a move in a particular game, move made in a particular game, or a request to initiate a game. So that we let's call that a game request. That comes to the game service, and that what it does next is it looks up existing game. So if the game exists, great. If it doesn't exist, no. What we will do, look up if the game exists. If it doesn't exist, it returns right away. Yeah, so that's the whole point of the game cache. So we can do that, and once the game is completed is when it will be written to this. Right, completed game. Actually, hold on, yeah. once a game is completed, it will pull the game data and write that to the game database, and this will be to fetch completed games. Yeah, that's about the game DB. Missing something? Okay, that's 40 minutes of the 45 minutes. So at this point, I would go on explaining my design a little more. So let me do that. So in this case, I have the user interface that talks to the load balancer. So it could be one of three things. One is user management in terms of sign up and login is handled here. Any profile updates is handled in the user management service. The auth service handles the login and the auth token validation. So for the and the game service handles any game requests. That could mean creating a new game or looking up an existing game. So creation and looking up an existing game and updating an existing game is also is all stored in the game cache. The data for all of that is stored in the game cache. What is stored in the game database is completed games. So when a game is marked completed, that is pulled from the cache, and by the game service it is pushed into the game DB. So that way this is long-term storage, and it has every ongoing game is in the game cache. For that, we see I did not do the math for that, but since it's under the 45 minutes, I can talk about that at this point. So I would say each game is 1.4 KB, and at peak usage we have 8 million users, and 8 million users would mean 4 million games. So that would be at most 4 million times 1.4 KB. That's 1.4 GB times 4. So that would be 14 fours, 56. So 1.4 GB times 4, right? So 5.6 GB is the cache that we would need to store the game data at peak usage, which is not a lot. So 5.6 GB of cache is good enough for us to save all of the game data at peak usage. So at normal times it would be way less. So that's the cache game data. Moving on to the user management service, right? So the flow here is the load balancer makes let's assume it's a sign up request. So during sign up, the user will want to check for existing usernames so that it becomes a unique username. Instead of hitting the database for all of that, the username checks are done through username cache. All the usernames are stored in the username cache, and if it's not in the username cache, the cache looks up the database and pulls it from the database. And if it's not found in the database, then that's just returned to the user management service, and then the user knows that it's a unique username and the username can be assigned to the user. If it is found either in the database or in the cache, if it's found in the cache, then without hitting the database, the user management service is aware of it now, and that goes back to the user, and the user has to choose a new username. If it's not in the cache looks up the user DB, pulls up the username from the user DB, and that's saved in the username cache, and sent back to the user saying this username already exists. So the next time another user tries to create the account with the same username, it's now updated in the cache, so it won't go to the database again. That's the purpose of using this cache here. It's purely for sign up reasons, to reduce the load on the database, reduce the number of database hits made here. That's that. And any creation or updation of the user data is directly done from the user management service to the database and not through the cache, because any updation and creation is a one-time thing, and that is not something that the user can update or create a record, and it does not. Only creation of a record needs to be updated here. But the next time that anyone tries to fetch that username, the username cache will make one single request to the database and get it. So that's a one-time thing. Oh, I ran out of the 5 minutes at this point. Yeah, so I will. That's my 45 minutes. Just 2 more minutes. Yeah. So the only time that we will need the user details to go to the database and also be updated in the cache is when the user sign up takes place. The user sign up means that the user DB is updated to a new record is added to the user DB, and that is fetched the next time that the user tries to interact with the system. So it looks up the cache, and that's not found because it was recently added directly to the database. So the cache looks up the DB and fetches that information. And if for some reason you want to directly you need to so the one of the main reasons for the user DB is auth. So that is going to be a read-only fetch from the database directly to the auth service. So every time someone tries to log in, that's going to be done as a read from the user database. So that's the most current data. And once that's done, the auth service generates a token, and that's written to the auth DB. The next time someone tries to validate that token, so once it's written to the database, the same thing's returned to the load balancer and the user. And the next time the user needs to validate, the user sends the auth token to the load balancer, and that goes to the auth service. And this service looks it up in the cache. It doesn't find it, so then it moves to the auth DB, pulls that auth token, and sends it back to the auth service. The auth service validates it and then returns it. So that's the entire system. We've already covered the game service. Okay. So that took 47 minutes instead of 45. So I stopped designing at 40 minutes. So I spent 7 minutes explaining my design. Yeah, I will improve the timing on that.